Hello, in this episode, we'll introduce what explainable AI is. So this broadly belongs to machine learning interpretability, and it allows one to examine models basis on its decision-making processes, why they make a decision. There are reasons for why we want to have that. First is the increased reliance in AI, which oftentimes is a black box. We want to understand what's going on. By doing this, we ensure impartiality, detect some bias in the training set. Also, it provides a robustness, there's sometimes malicious perturbations that change the prediction. And if we understand why the reasoning came from, then it will be robust to this malicious attempt. It also ensures against only meaningful variables in for the output. Right? So here are some examples. For example, in regulating for AI trading, if there's some trades, but we suspect there's some insider trading, if the model can explain why they came out for the trade decision, then we can potentially check whether it has to do with insider trading or not. Also, medical imaging, these kind of the diagnostic images and why is it diagnosing it, and if we can highlight the reasons for those, it helps believing the result, isn't it? There are many types of machine learnings, and some are intrinsically interpretable. Linear regression is probably the most well-known one, but also trees like this. We can understand where it comes from, or the regression coefficients explain which coefficient does explain and how much it adds to predictability and such. But oftentimes in modern machine learning, we have deep neural networks. And here, oftentimes, it's very complicated to understand from which of the input, how it influences the output decision. Okay. And here are some intrinsically interpretable methods for deep learning. For example, the regularization for salience in map is one thing. So here's a sample of handwritten digits from MNIST. And sometimes the technique here, what people can employ is to, broadly speaking, check how it differs from the neighbors. And by doing that, it shows which pixel actually mattered for determining this is a digit 7, this is a digit 2, and such, isn't it? So it kind of shows which pixels were responsible for explaining and making the prediction. So that's one way to do it. There are also some local surrogate methods, oftentimes called LIME, which is local interpretable model agnostic explanations. It's a local model, so it tries to explain just one observation. And it's model agnostics that you can apply to any kind of model, like deep neural network and other things. What it does is that basically, in a very localized region near this point, they try to assume like this, it's in the locality, they perturb each explanatory variables and auto features, sometimes we call it, and then see how the predictions change. And so it's like having a magnifying glass here and then see how each factor changes. Okay. So that is one way to try it. It's localized method. So for the whole explanation, I think there are some alternative methods, but here is a fun example of how to LIME works. So here's an original image that a Labrador is playing a guitar. That's the original image. But if it predicted like I'm playing electric guitar, where's the electric guitar part? Well, the pixels that were highlighted are here. Which one explains an acoustic guitar? Those dots do. Which explains the Labrador? Those dots do. Isn't it? So this is sort of how LIME works. Some other features which are global explanations, relying on Shapley value. So they assign a feature importance weights based on game theory Shapley value, which is named after Lord Shapley, a Nobel winner for his theory. And it basically is how much was your marginal contribution is basically what the Shapley value tries to capture. For example, what it does is that, so here's a value that is coming from a group of, let's say, people, S, and an individual I. So the whole value with all them together is we subtract the value of what obtained from S, okay, that will do a marginal contribution of I for that particular combination of people. But then in a large group, there are many, many different combinations of S. So, and there are probabilities of that group forming. So the probability weighted of this marginal contribution all summed together will be the Shapley value. I guess here's an example. For example, there's a fundraiser cookie sale like Larry, Mary, and Nancy does it. Okay, so, and we individually measure the sales, like Larry had 10, sold 10, Mary sold 20, Nancy 25, Larry and Mary 40, Larry and Nancy 30, Mary and Nancy 50, Larry, Mary, Nancy 90. Okay, so what's the incremental? I guess we can count like in a different order and ignore the people afterwards. So only count people coming before Larry, right? And so here it's just Larry. It doesn't matter whether Nancy or Mary came afterwards. It's just Larry's measured here. And that's Larry's value minus the coalition, the rest of the people participating, which is none. So it's just 10, same here. When Mary, Larry, Nancy's here, so Nancy comes after Larry, so let's ignore that. So we have Mary and Larry together, 40. Subtract that from Mary's sole contribution, which is 20. So Larry's contribution is 20. And then Nancy, Larry, Mary, similarly, it's together they have 30. And just Nancy part is 25, so it's just 5. Mary, Larry, Nancy, it's 90 minus. Then Mary, Nancy gets 50, so it's 40. And the same with this combination, it's 40 here. So at the end of the day, the average of this 10, 10, 25, 5, 40, 40 will be 20.8, and that's the Shapley value. So you get the idea. That's a marginal contribution, the average of the marginal contribution of Larry, given all possible combinations of coalitions. So the results often shows up like this. So here is some example, and here are some features like tax rate and many things. And here this each feature's impact based on Shapley value estimation. And you can plot it even in a signed way. Some factors relative to this, whatever that estimate is, comes in a negative influence, some come with a positive influence, and you can show it in a Shapley plot here. So this is sort of showing some examples of explainability, explainable AI, and show the techniques here. Okay. Thank you for watching this episode.